Today in physics, we're going to talk about center of mass. So I have here a couple of things. So I'm going to demonstrate center of mass using this lever here, and then I'm going to do a center of mass. We'll do the same problem on the board, and you'll see how to solve it, at least for this one particular example. So what I have here is I have a lever. It's clipped right here in the center, and the way levers work, if you put the same torque on this side as this side, they'll give it opposite rotations, then it will stay level. How is this going to help us with center of mass? Well, if you have two objects, let's say that are hanging from each side, regardless of where they are, if it's balanced, then the center of mass ends up being in the middle here, because the way you calculate center of mass has to do with how much mass there is and how far away it is from all of the other masses. So we can demonstrate that. So if I have, let's say, a person here, so I have a person, you can see I take a little person to this mass here. And obviously if I put it in the center, it's not going to lean either way because the center of mass would be, well, right there. If I take this person and I hang them, say at this distance out here, then when I let this go, it's going to pull it down, right? So the center of mass is over here, which causes this torque that you're seeing. So what we're going to do is we're going to do the example of the center of mass of a person with a boat, okay? So here's my canoe for the person. So I'm using, as you can see here, 3 weights for the boat. So the boat will be 3 times as massive as the person in this example. So to find the center of mass, I'm going to first of all state that my problem is the person is going to start at one end of the boat. Okay, so the problem is if the person starts here and let's say they walk to the other end of the boat down here, how far is the boat going to move? So if the canoe is just sitting, let's say, on a lake, it's not tied up or anything, the person will start at one end and walk to the other end. Now, if this was the ground, it's pretty obvious that this is all that's going to happen. But when the boat is sitting on the lake, it turns out that since the boat is not connected to anything, there's essentially no friction with the water, as this person walks down this way, all of the forces involved in my system are just between the boat and the person. And if my system is the boat and the person, then as this person moves this way, he has to push the boat in this direction every time he takes a step. Because this is an internal force, right? So when you look at Newton's laws, they talk about things like net force. Well, net force would be an external force on your system. So if my forces are completely internal, what Newton's laws tell us is that the motion of an object, whatever it's doing, will keep doing that unless acted upon by an external force. Well, if the objects are just sitting there, like they will be at the beginning of this problem, then as the person walks from one end to the other, there is no net external force. So the center of mass of the system will remain constant. Okay, so let's look at how that might work. So I'm going to hang these guys up here. So I'm going to put the boat here at 10 centimeters from the center of the lever. And so obviously it wants to come down. So now I'm going to put my person on the other end here. I've done everything. There we go. Got a person, got a boat. It's a little bit taller so it doesn't hang out in there. Alright. So I've got essentially, I don't know what I'm talking here. I don't want to hang straight, but you guys get the idea. So I'm having to hold this so this isn't flat forward. I'll leave it alone here in a second. So you can see here that if I put the boat at a distance of 10 centimeters, and it has roughly 3 times the mass as this person, to make this thing balance, this ends up being 10 centimeters times whatever this mass is. This ends up being 30 centimeters times whatever that mass is. So essentially this is 3 times the mass, so this has to make up for it with 3 times the distance. So, what's going on in our scenario? Well, the scenario is this guy is going to start at this end, and he's going to walk down to the other end of the boat. Well, as this guy starts to move, let's say he moves to just 20 centimeters now. Right? When he moves here, the problem is, if I was to let go of this, this thing is going to rotate downwards. Like, if I let it go, it's going to end up down here like this, because it's heavier on that side. So remember that the system here, let's put him back to start. So the system is the person and the boat. There's no there's no external forces. So as this person moves this way, the boat will start to move in the opposite direction. But the problem is, since the person weighs so much less than the boat in this case, as the person starts to move, the boat will start to move in the opposite direction, but not as fast. So essentially, if one moves, the other one has to move as well. And so what's interesting here is, let's say that his final destination is the other end of the boat. Well, at some point in time, the person will be in the middle of the boat. And this person's center of mass is, well, in the center of the person, and the center of mass of the boat is in the center of the boat. So what's interesting is that when this person goes to walk from one end of the boat to the other end, when he's in the middle, the center of mass of the boat and the center of mass of the person will be in the same place. And so it's very obvious that the center of mass for both of them, when they're together, is right here in the center. Well, if we go back to how it was at the beginning, you go, okay, well, how was this in the beginning? So I'll turn it. Where's our center of mass to begin with? Now, because I'm doing this on this lever, it should be obvious that the center of mass is, well, where this pole is. Okay? That center of mass is not going to move, because in the scenario I'm giving you, all of these forces are internal. So the center of mass, wherever it is going to remain constant. So to find the center of mass mathematically, what we would do is we would use our formula as given in our equation sheet. X, center mass, so we're only considering one dimension, in this case horizontal, is the sum of xi mi divided by your total mass. So this is for each particular mass. So for one object, the center mass is obviously wherever the center mass of that object is. For two objects, we can do this. So in order to find the center of mass, I have to establish a coordinate system. So you can establish a coordinate system as anything as zero, whatever you want to pick. But what I think is an interesting choice is to pick the center of mass of either the boat or the person. So the center mass of the boat, I'll mark right here, so we can see it, and center mass of the person as well, over here. I don't think you'll be able to see that. I'll just draw along this line. It should be in the center of the person, but I taped it to the side of the weight. So here, we can see that center mass should be between these two objects. And since this was 3 times as massive, it should be closer to this. So what I'm going to do is I'm going to pick the center of mass to be, or my 0, to be the center of mass of the boat. So if I do that, I can draw my situation here. So I've got my, let's say, canoe, I've got my person, and the person weighs or has a mass of 3 times that of the boat. So this is the center of mass of the boat, this is the center of mass of the person. So I'm going to pick this spot right here to be my origin. Okay, so this is 0, right? So if I want to find the center mass, I need 2 things, a distance and a mass. So let's say that the distance is going to be measured by that. Let's say the mass of the person is 1 kilogram. So I'll say the mass of the person is 1 kilogram, and they're at a certain distance. So they're at centimeters. Let's go with whatever. Yeah. So that's at 30 centimeters. So the person is, well, not 30 centimeters. He's 30 centimeters from the center, but how far is he from here? Well, if each one of these is 10, he's obviously 40 centimeters from the center of mass of the boat, and that's what I've established as my zero right here. The center of mass of the boat currently is. So I'll do this times 40 centimeters. Then I should add some the mass of the boat, so that would be 3 kilograms. It's 3 times the mass of the person. And I'm going to multiply times its distance from zero. Well, since I picked the center of mass of the boat as my zero position, this number would be 0. Now, to find the total mass, we just add them up. So I do 1 kilogram plus 3 kilograms. So my XCM is going to be calculated as 1 times 40, so this would be 40 kilogram centimeters plus 0 divided by 4 kilograms. So my XCM, X center mass, ends up being, well, 40 divided by 4 would be 10 centimeters. And so that's 10 centimeters, in this case, in the positive direction. So I didn't quite establish that. But since I said he's 40 centimeters, I call it positive. So I'm starting this. This is the positive direction, right? So this would be my negative direction. So that's the center of mass. That's 10 centimeters in the positive direction, which indeed we see that's where it is. So we can do this again when we move the person to the middle, and we move the boat, the cumbersome boat, to the middle. Now I could do that calculation again, but since they're both at 0, remember my origin is here right now, okay? So if this is my origin, then the center of mass of the person is 10 centimeters to the left, and the center mass of the boat is also 10 centimeters to the left. So obviously the center mass of the system is going to be 10 centimeters to the left of where the boat started. But let's keep going. What would happen if we got the person to the other end of the boat? Where would they end up? Well, it's a mirror image of what we started with. So we could guess that they should be in the opposite spots. So this thing should be a 10, and he should go to 30 down here. And the question is, does this balance? Well, indeed, it seems to balance. So now you've got the person down here at this end. So where's the center of mass in that case? Well, we could do another calculation for the center of mass. It's going to look very similar as an XCM, but I should stick to my coordinate system that I've established earlier. So this is going to be a little tricky, so bear with me. If this is my center of mass, this person is going to be to the negative side. So we say negative 10, 20. So the person is going to be negative 20 centimeters. Still has a kit mass of 1 kilogram, plus, so over a total of 4 kilograms. 3 kilograms for the boat, and its center of mass is how far from our origin. If this is our origin, we have 10, 20. It's at 20 to the right of our origin. All right? So we end up with saying XCM is negative 20 plus 3 times 2 is 60 centimeters. Centimeters times kilograms. Over 4 kilograms. So 20 minus 60 would be 40. Okay, so this would be 40 kilogram centimeters over 4 kilograms, which ends up with, again, 10 centimeters for a center of mass. So 10 positive 10, so it's in the same place as it was before. So we've just proved that. What's the point of this? Well, when you get problems, it's probably not going to ask you just to calculate the center of mass. That's pretty easy. What the problems are going to ask you to do is something like this, where the person starts at one end and moves to the other. So the first thing you need to know is that if all of the forces are internal, then the center of mass of the system will stay the same. So the first thing you do in a situation like that is find that center of mass. Okay, so that would be this first step that we took up here. So we want to find that center of mass, because that center of mass is not going to move through the situation. Okay, so that was the first thing we did. Now the person moved, to the middle, then eventually wound up at the other end. So then we end up with a mirrored situation of what we had before. So we go, okay, what kind of question are you going to be asked about this? Well, usually the questions are, okay, well, if the person moves, say, from this end of the boat to the other end, how far does the canoe move? Okay, well, we actually picked a smart coordinate system to start with, because since we started the center of mass, we started our 0 at the boat center of mass, which was right here. So in this setup, it's pretty obvious that the boat went from here to there. So the boat has traveled a distance of 20 centimeters in this case. How is that related to our center of mass? Well, it's obviously twice as far. Why is it twice as far? Well, remember that we started with this person down here, and the person moved from here all the way to the other end, okay? When the person did that, there was a point at which the person was in the same place as our center of mass. And because the center of mass doesn't move when there's no external forces, as the person walked this way, Newton's third law says, okay, for every action there's an equal and opposite reaction. So the person is walking this direction, they're pushing a force backwards, which is causing the boat to move backwards, okay? So as the person moves this way, the boat moves backwards. So when the person gets to the center of mass, well, then the boat also has to be at the center of mass, because there's only 2 objects in this case. So when they're both at the center of mass, how far has the boat gone? Well, the boat went from here to there. The boat traveled from where its center of mass originally was to the center of mass of the system. And then the second half is just a mirror image of that. So of course it's going to go twice as far. It started here with this far, and went back that way. And so that's always going to be true if you have a problem like this, where you have 2 objects and they're just interacting with each other. So the center mass is going to remain constant. And so whatever distance, let's say the boat is from the center, you can double that to figure out the distance that the boat actually traveled. Now for the person, it's actually the same thing. You can measure the distance the person moved from the center of mass. So in this case, the person moved, originally he was 40 centimeters from the center of mass. Then he moved to the other end of the boat, which means he moved twice as far. So in this case, if I knew that this guy started at 40 centimeters, so he's going to double that distance. So you might ask yourself, but he just walked to the other end of the boat. Well, it turns out if you measure this boat here, it may not be obvious, but this boat is longer than my rod here. It's longer by about 20 centimeters. And so as a result, the length of the boat is 80 centimeters in this case. So the person walked from one end of the boat to the other, length of the boat. And so you're probably not going to be asked that question. You're probably going to be asked, well, how far is the boat? Well, it's going to be twice the distance it is from the center of mass. Okay? So I'll probably record another video where we do 3 objects and see how they interact.